Risk and randomness is an incredibly important thing in artificial intelligence and machine learning, especially where there is some degree of uncertainty. So, mathematically speaking, the probability of an event is the likelihood, or better yet, using the phrase expected relative frequency that it will occur. So expected relative frequency presents a couple of important terms here. Expected means it's never guaranteed. And relative frequency means, well, frequency means how often, and relative frequency says, how often do we expect it out of how many times, so to speak. And this is an expectation, meaning that just because you toss a coin 10 times doesn't mean you'll get 5 heads and 5 tails. You would expect that, but that's not guaranteed. So the range, this interval probabilities are defined on, is from 0 to 1. So we could write it as a mathematical interval. 0% or 0.00% would mean guaranteed not to occur, and 1.0 or 100% would be guaranteed to occur, and then there is, of course, that gray area between 0 and 1. So, for instance, the probability of tossing a fair two-sided quarter with heads facing up is 0.50. Okay, so what does that mean? Well, if you toss a coin once, it doesn't mean you're going to get half head, half tail, right? It means that if you were to toss it many times, so theoretically, infinitely many times, 50% of the outcomes should be heads facing up. So every probability sort of comes as a triplet of two sets, and it comes as a triplet of concepts. There is something that we call the sample space, and that's the set of all possible outcomes in the context. So, if you toss a coin once, then you have two possible outcomes, and so one way we would do that is to list out just T and H for tails, heads, which would be the same thing as H comma T. Those are the two possible outcomes. A is the event of interest. So it's going to be some subset of the sample space. So for example, A could be the event that maybe we're going to win if we toss the coin and it comes up heads. And then to each event in the set of all possible events, a corresponding probability is assigned. And that's going to be, again, a value between 0 and 1. So think about this as a function. To each possible event, you are assigning a numerical value, whether or not that event itself is a numerical value. So let's now consider tossing a coin twice. And if you toss a coin twice, you can pretty quickly see there are 4 outcomes. And one quick way to think about probabilities, even if there are too many things to list out, is to sort of explore what can happen with something like a tree diagram, some sort of diagram that's visual. So if you toss the coin once, think about this as the root before anything has happened, and on the first toss you could get a head or a tail. So these would be 2 distinct possibilities for that toss number 1. And then let's just say you tossed a head on the first toss. Well, from there you could still get a head or a tail on the second toss. This would be for toss 2. And similarly, if you were to have tossed a tail for the first toss, you could still get heads or tails for the second. And now you can think about each of these branches as leading to a distinct outcome. So for example, if we start at toss 2 being heads, then we could trace that back to the root and see that that would lead us back to another head, which would be the outcome head-head, and then head-tail, tail-head, and tail-tail. So you can see there are 4 outcomes. And in this context, because of the mathematics that would play out, each of these 4 things should happen equally likely. So each of these events would get assigned a probability of 0.25. And one interesting thing to note is important thing to note is if you add up the probabilities of each of these events, you're going to get 1. And that's important, right? Because then that means we've accounted for every single possible outcome in the sample space. And if you take every outcome in the sample space and you don't get 1, well, then you're in a little bit of trouble, right? Because it means there's something that we haven't accounted for. We often have some sort of random variable of interest on our sample space. For example, we could define capital X to be the number of heads tossed into coin tosses? Well, let's look at the possible outcomes and say, well, if we toss the coin twice and we just look at our final outcome, like heads, and we ask ourselves how many heads were tossed in those two coins, well, you could see here there would be 2 heads, here there would be 0 heads, here there is 1 head, and here there is 1 head as well. Notice just the sequence is different on these last two. This is heads first, then tails, or you could toss a tails first and then a heads. So our random variable can be written as a set of the number of possible of the values that random variable can be assigned. Well, that random variable could be 0, it could be 1, or it could be 2. You can't toss more than 2 heads, and you can't toss fewer than 0 heads in 2 coin tosses. So the probability that x is equal to 0 and would be the situation where we get 2 tails. So that's the same thing as saying, what's the probability of tails? And we already know that that's 0.25. Probability that x equals 1 would be the situation where we get 1 tail, and that's actually the sum of 2 probabilities, which notice are non-overlapping. You can't have both of these things happen at the same time. They are distinct, so you would have to sum up their probabilities, and we would get 50% chance of getting exactly 1 tail, and then of course getting 2 heads, of getting exactly 1 head, and then the probability of getting exactly 2 heads is again 0.25. Once again, notice that if you add these probabilities up, you get 1.0, right? Because even though the probability that x equals 1 had 2 events bundled into it, and there are only 3 values of that random variable, that means that if you sum up the probabilities, you should account for everything that can happen. So that brings up this point that the sum of all probabilities of a random variable should always be 1.0. Now, what we've done here is we've just defined a probability distribution for this random variable. Just as the name emphasizes, it's how we distribute the probabilities to different values of the random variable. So in our case, we could actually look at this visually, and we will in a moment. We could actually list out the probabilities themselves, or we could actually use something that looks kind of like a bar graph called a histogram to denote those probabilities. So what we've taken a look at so far only involves discrete probabilities. These situations, notice, involve a random variable that can take on a finite number of outcomes. It's also possible that you have countably infinite number of outcomes. For example, let's say you keep tossing a coin until you get a head. Well, theoretically, that you could toss a coin infinitely many times and not get a head. I know that would be highly unlikely if it's a fair coin, but the number of times you have to toss it in order to get your first head, that could be countably infinite, because you could get it on your first toss, your second toss, your third toss, your fourth toss, all the way on up. On the other hand, a continuous probability involves a random variable that can take on any value within a range or interval. So we'll take a look at an example of both. Typically we'll write the probability of a random variable as the probability that capital X equals little x. So this is the actual value, and this right here is from the set of all possible values, what's the probability that from the set we get the specific value. And that's called the probability mass function. So each of these values in your probability is going to be associated with a mass. So let's think we'll come back to this in a moment. We'll take a look at the coin toss example, and we'll illustrate the probability mass function more visually. Now, we also have a function that accumulates probabilities for all x less than or equal to x, and that's called the cumulative density function, because again, we accumulate, or cumulative mass function, if you wish, for this probability, particular discrete probability. Now, again, that constraint is that if you add up all of the events in capital X, you add up all their probabilities. I should have written here that the sum of all of the probabilities for every event or every value of our random variable has to equal 1 as before. And let's consider the previous coin toss example. So let me go ahead and lay out the probability mass function as a probability distribution. So here we had 3 outcomes, and I'm just going to write them like this. 0, 1, and 2, those were our 3 values. And to each of these, we had associated a probability. And since there were only 2, I'll list them like this. So the probability of getting 0 heads was 0.25, and then 0.5 for getting 1 head, because there are 2 ways we could do that, and then 0.25. So here's our probability distribution, just done visually, right? We've already listed them out, where we said the probability that x takes on a value of 0, meaning no heads, is 0.25. The probability that we get exactly 1 head is 0.50, and the probability that x equals 2 is equal to 0.25. So these sum up to 1, and again, that's very, very important. So here's a list of the probabilities. Here's just a sketch of the probabilities. Now, if you actually looked at the probability mass function, without getting too much into the details here, the probability that x is equal to little x, in our case, would be first of all, the number of ways to get out of 2 coin tosses to get exactly, well, let's do this. To get exactly 1 head, let's think about how we would compute this. So 0 heads. One way to think about this would be to say, well, here I have my 2 outcomes, and what I want to do is at random, or to point out all the possible ways that this could happen, is out of 2 slots, pick 0 of them and put a head in there. Okay, well, that's a combination, and so we want to ask, if I have 2 slots, how many ways can I pick 0 of them into which to put a head? And the probability of getting 0 heads is 0.5 to the 0, but then that means that I would need 2 tails, which would be 0.5 squared. And so this would give me that probability that x is equal to 0. The probability that I get exactly 1 head would be to say, all right, out of these 2, how many different ways are there for me to pick from the 2 slots, 1 of them, and place a head in there? Well, I could either put the head here, or I could put the head here. And so there would be 2 ways to do that. I want 1 head and 1 tail. And so in general, we would say that the probability that x equals little x is 2 combination, whatever that value of little x is. So in this case it was 0, in this case it was 1. 0.5, so you want little x heads, and then you want, since you have 2 outcomes, you want 2 minus x tails. So this is actually called a binomial distribution function, and this is the probability mass for this case. And then to get the cumulative function, the probability that capital X is less than or equal to little x, well, then you would have to add the probability that x is equal to 0 plus ... plus the probability that x is equal to little x. So again, imagine that, here we have 0, 1, or 2, and we want to know what's the probability that x equals 2, let's say. Well, then the probability that x is less than or equal to 2 would be this probability plus this probability plus this probability. And so we would need to add all of those together up until we have reached the particular value of x. Now, for continuous random variables, very similar, except you can't add them up because you're going to have some sort of continuous function. And that continuous function is going to involve an integral. So we'll take a look at an example here briefly, but remember, an integral is just a sum, but it's over a continuous set of values. So instead of having just 0, 1, or 2, imagine that we could have any value between 0 and 2. Meaning, from 0 to 2, here's this interval, and if this is a continuous interval, then anything in between can happen. And also we should point out that the probability of a single point is 0. Okay, this is very important because if you have a continuous set of values, the probability that you get exactly some number, between 0 and 2, let's say 0.8956341, right? There are infinitely many values in here, so the probability that you get any one of them is essentially 1 out of infinitely many numbers that fall between 0 and 2 on a continuous scale. And so that is equal to 0. Now let's take a look at an example that will really pin this point home. Let's say that we have bus arrival times, and we're going to assume that the bus arrives uniformly, maybe not exactly when it's supposed to. Maybe it's supposed to arrive at 1:10, let's say, but it sometimes arrives a little bit earlier, sometimes it arrives a little bit later, but it arrives uniformly within a 10-minute time frame. So again, let's take a look at the probability. In this case, this should be called a probability density function when it's continuous. That's just a naming detail, the difference. We call these PDFs. And so here we'll have x. So let's just define x to be the bus arrival time. So it's basically the set of all times. And we know that it's going to arrive somewhere between 1:05 all the way up to 1:15, including possibly those two endpoints. It could arrive at 1:05 or at 1:15. Now let's just say, here's my distribution, and then now I'm not going to have probabilities on this. I'm actually going to have densities, because if we add up a bunch of probabilities, and there are infinitely many of them, then we're going to get an infinite probability because we're going to be adding up infinitely many probabilities. So we actually have density on this scale. I know that didn't make sense. Let's go ahead and take a look at what I'm trying to say here. 1:05 all the way up to 1:15. Now it's going to be a uniform probability, meaning that the probability won't change. That's what we mean by uniformly between. Okay, so this is going to be some function, and I'm just going to I'm going to draw lines here, but those lines aren't actually there. It's just a horizontal line. And then the area underneath here, the area should be 1.0 area, right? Because that's going to be the total probability. And we said that if you integrate all of the probabilities, in this case, for x being between 1:05 and 1:15. Now, really, we should make these, not times, but numerical values. For the sake of this illustration, it works fine. But if you say, what's the probability that the bus arrives somewhere between 1:05 and 1:15, you would say, well, it's 1, right? Now, what would f of x have to be? What would be this value that's uniform all the way across? Well, one way to actually figure that out, well, actually, let's define it this way. Let's say that instead of using the actual times, after 1:05. So rather than to have to actually do the physical time, we have numerical values, and it'll go 0 to 10, right? And this would be in minutes. So in minutes after 1:05, well, it could be 0 minutes after 1:05, which would be 1:05, all the way up to 10 minutes after 1:05, which would be 1:15. Now here's, say, 0, here's 10, and so the integral from 0 to 10 should be 1. All right, well, I have to ask myself, what would have to be the height of this? And without doing all of the calculus, the function that we would get here, well, first of all, it would be a constant, right? So 0 to 10 of some constant equals 1. Dx. So the integral of a constant would be cx evaluated from x equals 0 to x equals 10. And that has to equal 1, right? So here I'll have 10c minus 0c has to equal 1, which means 10c has to equal 1, which means c has to equal 1/10. So that tells me that this height right here has to be 1/10 all the way across. And that should make sense because if you take 1/10 times 10, you get exactly 1.0. So here our probability density function is f of x equals 1/10. It's a constant distribution. Now the CDF, the cumulative density function, remember that this is the probability that x is less than or equal to little x. And that would mean that we accumulate starting at 0 and going all the way up to little x of the function 1/10. All right, so the CDF in this case is this function, and you could take it one step further, and you could say it's 1/10 x evaluated on the interval from 0 to little x. Kind of sloppy notation. Let's call this x naught. And so that would be 1/10 x naught minus 1/10 of 0. And so there is your actual probability density function. So a lot of times we would say that f of little x is equal to, or f of x naught is equal to 1/10 times x naught. So if I wanted to know the probability that x is less than or equal to 8, well, then I could say it's the integral from 0 to 8, which would be, well, there's an 80% chance that it arrives fewer than, or sorry, less than or equal to 8 minutes after 1:05. Now, for instance, let's take a look at here. What's the probability that x is equal to, the bus arrives at 1:06? Well, that's the same thing as saying that the probability of x equals, that's 1 minute. And well, what's the probability that it arrives at exactly 1:06? Well, of course, there are, infinitely many times between 1:05 and 1:15, and so the probability that it arrives at exactly 1 minute after 1:05 is a 0% chance. Here, the probability that the bus arrives between 1:08, which would be 3 minutes after 1:05, and 6 minutes after 1:05, well, that would simply be the integral x goes from 3 to 6 of our function 1/10 dx. Now, it's pretty easy to think about it in terms of our function if you realize that it's pretty much just a length times width. So if I want the area from 3 all the way up to 6, I just have to sort of think about what's the area of that rectangle right there. And if you think about the fact that it's 3 units wide, this right here is 3 units wide. And then how tall is it? Well, we already said that that's 1/10. And so this answer will come out to 0.3. There's a 30% chance that it arrives between 3 and 6 minutes late. And of course, you can conduct that integral and you should get 0.3 as well. So that's a little bit into continuous and discrete probabilities. There are a lot of different types of well-known distributions, some of which we'll take a look at soon.